In this video, I will talk about the relative part of the Lagrangian. Now, in this video, I will talk about essentially the motion of object 2 with respect to object 1. Anytime you have two objects moving under the influence of their internal forces, then the motion is two-dimensional. Those two objects will always move on the same plane. Now, I do have a choice for what coordinates to use, and the one that makes our lives the easier are the polar coordinates. Now, I will use r and theta to describe the vector r that goes from 1 to 2, or in other words, the relative position vector of object 2 with respect to object 1. Now, I'm not going to be using any subscript here on r and theta, just to make the equations look a little bit more simple. Now, okay, let's see what our Lagrangian looks like. So I got L. This is essentially the contribution from the center of mass. This is the kinetic energy term of a particle that does not exist with mass equal to the reduced mass. And this is the speed, the time derivative of the relative position vector of object 2 with respect to object 1. Now, because I'm using r and theta to describe the vector r from 1 to 2, then the time derivative of this, or the speed, will also be expressed in r, theta, r dot, and theta dot. Now, from polar coordinates, I know that the speed is equal to r dot squared plus r squared theta dot squared. And because I have the square, this with the square root will cancel out. And then I have minus EP that depends on r and theta. Alright, now r and theta are my two generalized coordinates. So let's start with r. This quantity does not depend on r at all, but this one does, and this one does as well. So the partial derivative will be the 2 here will cancel out with the 1/2, so I have the reduced mass times r times theta dot squared minus the partial of EP with respect to r. Now let's see what we get for the other partial derivative with respect to theta. This term, of course, has no dependence on theta. The same thing for this one. It's only the potential energy that depends on theta. So I have minus the partial of EP with respect to theta. Now, this should be equal to the time derivative of the partial derivative of L with respect to theta dot. Now, there is no dependence on theta dot here. There is no dependence on theta dot there. The only dependence is here. So the 2 with the 1/2 will cancel out. So I have the reduced mass times r squared times theta dot. Now, here's the thing. If I make one assumption about the potential energy, if I claim that the potential energy has no theta dependence, then this partial derivative goes to 0. Okay, so this is a special case where my potential energy only depends only on the distance between the two particles. If that side is 0, then this becomes the reduced mass times r squared theta dot should be a constant. Should be a constant of the motion. And let's use the lowercase l to indicate that constant, whatever that is. Now let's go back to the previous equation. I found the partial derivative of the Lagrangian with respect to r. I'm not done yet, though, with this generalized coordinate. I still need to do d over dt, the partial of L with respect to r dot. And there is no dependence on r dot here. There is no dependence on r dot there. This is the only term that depends on r dot. And the 2 with the 1/2 will cancel out. So I have m times r dot. This is the reduced mass, not m. And this will be m r double dot. Now, this is the equation that I have for the r generalized coordinate. And one thing that I can do, since I found that this is a constant of the motion, I can use this expression and solve for theta dot and say theta dot is L over the reduced mass times r squared, and I can use this and plug it over here. Let's see what we get. So it should be theta dot squared and then I have minus the partial of the potential energy with respect to r. Now I did say that the potential energy does not depend on theta, it only depends on r, which means that this is no longer really a partial derivative. This is a dep over dr. And this is equal to the reduced mass times r double dot. And here, this reduced mass with the square will cancel out, and the r with the 4 will become a 3. So the equation becomes the reduced mass r double dot is equal to minus dep over dr plus L squared the reduced mass times r cubed. Now this expression does remind us Newton's second law. Okay. On the left side I have m mass, not m1, not m2. I have m mass times the second time derivative of r. So this is, if you want, what resembles what is mass times acceleration. And on the right side, I have minus the gradient, minus the derivative of the potential energy with respect to r. And this is a term that comes from a force. This is the conservative force that gives rise to the potential energy I have in the system. But in addition to the force that I have that is acting on 1 and 2, I also have one more term here, L squared over the reduced mass r cubed. This one does not have a physical, or this is not due to a force. Now, what it is important, it is useful to think about what we've done so far. I said when I started this, I was describing the motion of object 1 and object 2 with their two position vectors r1 and r2. Okay, and I had my coordinate system here, and I was observing the motion of 1 and 2. If in that case, all I had to do was to consider the interaction between the two, the force that is acting from 2 on 1 and from 1 to 2. Now, what I've done here with all of this work, I have been able to transform this the original problem to a problem where object 1 stays stationary, it is not moving. If you want, the observer, me, is at the location of object 1, and I am looking at how object 2 moves with respect to me, with the observer with respect to object 1. But to do that, to study the motion of object 2 when the observer is at the location of object 1, I should not only include the force that 1 exerts on 2, but I also need to add one more term. All right, so this is what I get for the r generalized variable, and this is what I got for theta.